High-technology catastrophes are the predictable result of systemic decay. They represent the final collapse of a complex system under sustained, unaddressed stress. On January 28, 1986, 73 seconds into flight STS-51L, the Space Shuttle Challenger disintegrated over the Atlantic Ocean, resulting in the loss of the vehicle and all 7 crew members. The physical failure originated in a synthetic rubber seal, an elastomeric O-ring, inside the right solid rocket booster. This vulnerability was a known design flaw that engineers had tracked through years of testing. This hardware flaw persisted through a process of organizational failure. Over a decade of operations, project management incrementally redefined the structural hazard as an acceptable parameter of flight. The disaster is a study in socio-technical failure. It shows the outcome when an institutional culture subordinates physical engineering limits to administrative goals. To achieve liftoff, the Space Shuttle relied on twin solid rocket boosters. These 149-foot steel cylinders were manufactured in independent segments. Once on the launch pad, they were assembled vertically using field joints, specifically a mated tang and clevis configuration. Inside each field joint was a double-bore seal. 2 synthetic rubber O-rings were seated in parallel grooves inside the clevis. To shield these seals from 5,000-degree combustion gases, technicians packed the interior gap with asbestos-filled, heat-resistant putty. Upon motor ignition, the internal pressure inside the booster instantly spikes to over 900 psi. This immense force causes the massive steel casing to physically swell outward. This swelling initiates a structural phenomenon known as joint rotation. As the steel walls expand, the tang and clevis bend away from each other. This motion pulls the mating surfaces apart, expanding the physical gap where the O-rings are seated. For the joint to remain sealed, the rubber had to exhibit hyper-elastic resiliency. They needed to instantly expand, shifting within milliseconds, to track the widening gap and maintain a physical barrier against the hot gas. This entire mechanical sequence relies strictly on the elasticity of the rubber. On the morning of January 28, 1986, the launch site temperature dropped to 29 degrees Fahrenheit, 15 degrees lower than any previous shuttle launch. This line graph maps the glass transition temperature for polymers. The specific rubber used for the shuttle's O-rings has a critical limit at 50 degrees Fahrenheit. Below this mark, the material suffers a severe drop-off in resiliency. At 29 degrees, the freezing ambient air pushed the O-rings far past their glass transition threshold. The rubber transformed from a pliable elastomer into a stiff, brittle, glassy state. It was physically incapable of tracking the joint rotation. Because the thermodynamic limits of the polymer were exceeded, the material could not perform its mechanical function. The physical seal was broken before the rockets were ever ignited. At just 0.678 seconds into the flight, launch cameras recorded the physical consequence of that rigid rubber: dark gray smoke violently blowing past the aft field joint of the right booster. Over the next 2 seconds, 8 distinctive black smoke puffs erupted from the joint. This frequency, 4 times per second, exactly matched the structural load dynamics of the ascending shuttle stack. The field joint was mechanically breathing, flexing open and allowing 5,000-degree propellant gas to burn straight through the seal. Despite this severe initial breach, the leak abruptly stopped. Aluminum oxide slag, a solid byproduct of the burning rocket propellant, was driven into the joint gap by the internal pressure. This debris acted as a makeshift seal. Had the flight conditions remained stable, this slag plug would have held for the duration of the 2-minute booster burn. Between 37 and 64 seconds past launch, Challenger encountered the most severe high-altitude wind shear ever recorded on a shuttle flight. The spacecraft's thrust vector control systems reacted continuously to keep the vehicle on its trajectory. These steering corrections induced violent structural flexing across the entire shuttle stack. This mechanical shaking physically shattered and dislodged the fragile slag plug from the joint. With the barrier gone, a continuous beam of fire erupted from the side of the booster. Deflected backward by the aerodynamic slipstream, this blowtorch flame severed the lower strut, attaching the right booster to the orange external tank. The booster broke free, pivoted, and crashed directly into the liquid hydrogen fuel section. The resulting structural collapse forced the vehicle out of its profile, destroying the shuttle stack at forces exceeding 20 Gs. Every physical element, the thermodynamics of the rubber, the pressure dynamics of the combustion, and aerodynamic loads on the airframe, operated exactly according to the laws of physics. The flight hardware did not behave unpredictably. The failure was strictly the human decision to authorize operation outside of known physical parameters. To understand why that decision was made, we must apply the work of sociologist Diane Vaughan, who defined NASA's internal culture through the concept of the normalization of deviance. When an organization operates a system with anomalies and returns safely, its internal risk baseline drifts. During the second shuttle mission, engineers documented in-flight erosion of the primary O-ring. Because the shuttle landed safely, management incrementally redefined this physical damage as an acceptable flight risk. This table outlines the official severity of that drift. In December 1982, testing proved that joint rotation prevented the secondary O-ring from sealing reliably if the primary seal failed. Because of this, the joint was downgraded from Criticality 1R, a redundant system, to Criticality 1, meaning its failure would result in the loss of the vehicle. Despite this catastrophic official classification, a culture of structural secrecy took hold. NASA and contractor managers continued to circulate informal memos discussing the secondary O-ring as a reliable safety net, actively ignoring their own official engineering requirements. This institutional disconnect culminated on the evening of January 27, 1986. Reviewing the cold weather forecasts, the contractor's engineering team issued a unanimous, formal recommendation: do not launch below 53 degrees. The response from NASA management inverted the foundational standard of system safety. Instead of accepting the burden to prove the system was safe to fly, management demanded the engineers empirically prove a freeze would guarantee a failure. Pressured by their primary customer, the contractor's corporate executives called a private caucus, excluding their working engineers. When the vice president of engineering continued to oppose the launch, the general manager issued a precise directive: take off your engineering hat and put on your management hat. By shifting to a management frame, the executive's perceived obligation moved from hardware safety to protecting schedule momentum and commercial relationships. Empirical physical data was subordinated to obedience to authority, and the contractor officially approved the launch. Following the disaster, the shuttle fleet was grounded for 32 months. NASA was forced to completely overhaul its safety organization and redesign the solid rocket boosters, producing the redesigned solid rocket motor, or RSRM. To solve the geometric flaw, the redesigned joint incorporated a metal capture latch, drastically reducing structural deflection. The unpredictable putty was replaced by a rubber J-leg relief flap. Upon ignition, internal gas pressure presses the flap tightly against the insulation, cutting off the gas flow. To control the thermodynamics, external strip heaters and weather seals were installed around every field joint. These systems guaranteed the O-rings would maintain a minimum temperature of 75 degrees Fahrenheit, ensuring material elasticity regardless of ambient weather conditions. 17 years after Challenger, the Space Shuttle Columbia broke apart during atmospheric re-entry. NASA had again normalized a documented flight deviation, this time accepting foam shedding as a routine occurrence rather than a warning sign of systemic failure. The legacy of these disasters establishes strict rules for managing complex systems. First, the burden of safety must never be inverted. A high-risk system must be assumed compromised until empirical data proves it is safe. Second, technical engineering authority must be completely decoupled from schedule and budget. If a safety office relies on program management for its funding or reporting structure, its critical warnings will eventually be compromised by commercial pressure. The laws of thermodynamics, structural mechanics, and material limits are absolute. They do not negotiate with flight manifests or executive commands. When an organization's hierarchy demands that engineering authority yield to management goals, catastrophic failure becomes an inevitability.